All right, hi. I'm Kristen Thyng, and I'd like to talk to you a little bit about color maps. Perhaps you heard a talk a couple days ago from Nathaniel Smith and Stefan van der Walt about color maps. And if so, great. If not, you should check the video out online because it's a great resource. I'm looking to kind of give you a review of that or tell you a little bit about that if you weren't there. And then talk about how to think about color maps for your own domain, what sorts of things to be thinking about in your own day-to-day work if you use color in your plots. Okay, so why do we care about color maps? So I have the same information plotted here in 4 different color maps. In the top left, we have grayscale, which in some sense is the best we can get for kind of a true representation of the information. It's just black to white grayscale linearly increasing. And this is kind of a basic look at the information that we have here. Next, we have jet, which everybody likes to hate on, and there's a lot of good reasons to. I'm going to add in a little bit of my own. As I said, it's the same information, but where I have arrows here, we see some sharp gradients in the color that make it look like there are actually like plateaus here and sharp gradients next door that really aren't there when we compare with the grayscale map. So as I've said here, jet can add in fake information, which you are just not going to want to do in your application, I'm sure. In the bottom left, we have a Matplotlib color map, yellow, green, blue. And it does a very good job, I think. So if you compare it with the grayscale above it, you see really generally the same information, but we've added some color, which can be both helpful for trying to show the audience what you're trying to get at, and it's also visually pleasing to be able to have different colors involved. I will say that it looks like we're maybe washing out some of the middle here. The bottom right, I think, is a slightly improved version of yellow, green, blue. And we're going to talk a little bit more about the details there, but we can see there's a little more detail visible in the center that was a little washed out on the other map. And as Nathaniel said a couple days ago, the use of jet threatens the health of you and those around you. So if nothing else, there's actually science to prove that. Okay, so what are a few considerations? There are a lot of considerations we could talk about when choosing your own color map. I'd like to just pick out a few kind of big picture ones, and then I'm going to talk about domain specific. So to start, what kind of data do you have? And here are 3 types of categories you might be thinking about. Sequential, so when you have information that's just basically starting somewhere and increasing in value in a regular way, so something like that I would think about in this regard would be temperature or salinity. You're just thinking about increases in that field, as opposed to something that might be diverging around a critical value. So for me, something like velocity, you'd be thinking about where's 0 and what's going positive from there and negative from there. So that would be a diverging color map you'd want, presumably to represent that information well. I've also stuck in here qualitative or something where maybe categorical, the sort of thing I'm kind of mixing up to a little bit there, but I don't really use these. But this would be maybe something where you have bar plots or something that you don't necessarily need to be thinking about a direct relationship between the different colors. So I think mostly about these sequential and diverging color maps here. Another thing to think about is colorblindness. About 10% of men in certain parts of the world have some level of colorblindness. And so there's no reason to preemptively filter out a number of your viewers. So we want to just be conscientious of this. And this helpful image here just shows what that at least in the severe form, one of these types of color blindness can lead to. We see that about this green and this red kind of translate to these colors that are pretty similar here. So in general, I think just best to avoid red and green together when possible. Okay, so perceptual accuracy. This is tying in very specifically with that Nathaniel Smith and Stefan van der Walt talk the other day. So they've put together this tool that I'm showing some snapshots from here. And I'm just going to step you through a few different pieces over different slides. So what I'm showing here is the gray color map again. So that's what's shown here. Straightforward. When you print it in black and white, sure enough, it's very similar for grayscale. And this plot here is showing the perceptual change across the color map. And so what we're thinking about here is the color space used to represent color, in this case, CAM02UCS, I believe is the name, has this great property where the Euclidean distance in color space is equivalent to our perceptual distance or perceptual changes for people. So we can look at the color map in 3D color space for this color space and look at how the distances between the dots along the color map are changing. And we're looking for a horizontal line here, basically. We want to have uniform perceptual change as we step through this color map. And that's going to keep us so that we see, a change in values that are being represented down here in the color map as being about equal to changes that we're seeing up here in the color map, so that we're seeing that information properly. So gray has that pretty well. There's a little delta here, it looks like, but it looks pretty uniform there. That's good. Here's jet, just to show you how that looks. And we do see that it jumps around a fair amount. There's the color map, and also worth noting black and white. If you're using this sequentially and you're expecting blue to look like it has a less value than red, and then you're printing your color map out to read a paper, that value and this value up here look very similar. Similarly, if you're thinking about diverging color maps and you have 0 somewhere in the middle, your negative values and your positive values are going to look really unclear here. Also involved in this tool are some plots to give you a feel for what the colorblind people with different degrees of colorblindness are seeing. And I'd just like to highlight these sharp perceptual changes. So we saw it in this image that I showed on the first slide there. Here's how that looks in this tool that we have, VizCM here at the bottom. You can find it yourself. Here's a sharp perceptual change, and sure enough, you can see that that's happening in the blue in the color map right above. Here's one in yellow, here's one in red, and these correspond to these sharp changes, and they correspond to some of these sharp features that we're seeing in the image accordingly. And you can also see them in color space, 3D color space as well. And so that's the sort of thing we want to avoid, right? Because that's adding in fake information. Okay, so this is moving forward to yellow, green, blue, one of the Matplotlib color maps. You can see that it has some jumps here, perceptual jumps, but the y-axis is much smaller. But for example, right here, there's a jump and then a relative flat. You can see that in 3D space. And I think that's what's leading to some of this appearing to be washed out relative to what happens just before it in the color map. So I went ahead and I used their tool, and I tried to essentially recreate yellow, green, blue, but with this property of having this uniform perceptual deltas through the color map being enforced by the tool. So you can see there's a horizontal line here representing this consistent perceptual change. You just can't see it because it's so straight and hidden there. The color map looks very similar, but now it has these nice smooth properties here. So uniform perceptual change, our black and white is looking good, smooth in 3D space, and we can see this little bit of detail that was kind of washed out in the other case. Colorblind, okay. So this is what the tool looks like. This just snapshot if you go and fiddle yourself, which once you get started is really easy to do, and you kind of pull these around and look at different cross sections and color space to make a color map of your own. So moving forward into domain-specific color maps. So what are we thinking for this? I'm thinking, at least, and I'm coming from Oceanography, I'm thinking consistency. So I probably am going to show a number of different plots through a presentation, and I can, I think, kind of train the audience to know what I'm talking about. I'm still going to say what I'm talking about, but it's hard to take in information quickly during a presentation. So if you use the same color map, a distinct color map for every time you plot salinity, people are going to understand that that's salinity, and that's good. It improves communication. The clear presentation enables visual connections. That'll come up on, I think, the next slide, where I show this in practice with data. It can be intuitive to audience. That'll be next too. And in the case of a package like I'm putting together and talking about as we go on here, You can be using color maps that other people have already thought about. So I've put together color maps to represent fields in oceanography that I think people would want to use, and I've tried to make it so that they have some certain good properties. So if you don't care about thinking about that, you can maybe use something that somebody else has already thought about that for you, and then in which case it's kind of vetted for you. So here are the color maps that I have at this time. I call it CM TAMU, I'm at Texas A&M, and these are the color maps here, kind of in a Matplotlib gallery style, and the different properties along the edge here. So for example, temperature on the top there has warmer colors for warmer temperature, colder for colder temperature, but it's not diverging, like red-blue, which goes red up to white in the middle and down to blue. A lot of people use for temperature, but I'd prefer not to, because when I've looked at temperature, I don't have a critical temperature that I'm looking at deviations above and below. I'm looking at a sequence of information from temperature. So in this case, I'm looking for having that intuitive feel, but also trying to properly represent the information I'm showing. Oxygen, for example, just goes linearly increased from dark gray to white, almost white, but I've changed the color at the bottom to a little bit of red to represent hypoxic conditions, where you have low oxygen, which is dangerous for marine life, and this is part of some studies people in my department look at. And on the other end, you can look at supersaturated oxygen conditions. So these are kind of these intuitive, domain-specific things that I'm thinking about. It might be simple, like green for chlorophyll. You know, why use rainbow for chlorophyll when green clearly screams plant life or chlorophyll? Turbidity is like dirt, so I have this, brown scales for that. And velocity, I don't necessarily know what would be intuitive for those colors, but I just want to note that I'm using a diverging color map, like I said before. We're going to be thinking about what's at 0 and going negative and positive from there. So here's some data we have. We have temperature, salinity, density, turbidity, oxygen, chlorophyll, and CDOM, organic matter, in the water column. Velocity here is at a different location, but also added in there. So I just wanted to note there's warmer, fresher water at the top, warmer here, fresher from the river. This is cross-section, so it's depth versus distance along these tracks that a ship is taking out in the Gulf of Mexico. So you're getting some Mississippi River water in here at the top near the sea surface. And there at the seabed, we have some low oxygen water highlighted in red a little bit. We have more turbid water at the seabed, where the dirt tends to be, the sediment tends to be brought up a little bit, and here we have that diverging color map. But I think by having these nicely laid out, they can look nice together, and you can really see the relationships between the different fields. So you can really see, like just visually see these connections between what's dark in certain places, light in certain places. It just makes it easier to communicate with yourself if you're looking at your data, and with other people that you're trying to tell about with your data. Here's a little bit more data to look at. More low oxygen water in this transect. We have very cold, salty ocean water at the seabed here. Some productivity, so some more chlorophyll near the surface here. And just some directions I want to go. I'm interested in adding more color maps as needed, basically. I'm thinking about bathymetry, maybe shades of blue. We're used to looking at maps where you have light blue near the coastline, darker blue in deeper water, so I'd probably want to stick with that convention. This is just a plot using that tool of the Blues Matplotlib color map. I haven't fiddled with it yet. Vorticity is a measure of the rotation in the water of a parcel of water. And for this, I would probably just want to choose a diverging color map that is different looking than some other color maps. Sea surface height, red and blue. So I said this is often used for temperature. I don't want to use it for temperature. I'd like to use it for something else that diverges. I think sea surface height would be a good candidate. And for speed, so a lot of times instead of plotting velocity, I'll look at speed, the magnitude of the velocity. And for that, I think I plan to just take the positive half of the velocity color map, for example, so that to keep that consistency as much as possible. Another consideration to think about is how you want to scale your color map. And one example that I've thought about this for is looking at the Mississippi River plume here in the Gulf of Mexico. Here's Louisiana, here's Texas. And we know from science that the expression of the river plume at the surface has approximately log scaled area. So in order to visualize the river plume area as well as possible and to show as much of those gradients as possible, I've stretched the color map here with log scale, and so we can see these gradients through the river plume better. So if you have a reason to change your color map, then there's something that you can to adjust it as needed there. Okay, so the package I've been talking about here is CM-TAMU color map package. I'd be happy if you're interested in talking to me about ocean color maps, but also think about your own color maps and what you're doing in your own field. Thank you. Interesting what? Interesting what? Interpolations? Normalizations. And for stretching it, you mean? I've only really thought about it for this one case. Yeah, but I think that would be good functionality to have available for when you do know something like that.
I like the idea of the domain-specific color map names, but it's instead of like a proliferation of domain-specific color map packages, there's something that can be done at a higher level to like guide users. It's harder.
Yeah, okay, so I forgot. The question here was maybe should we have a whole bunch of domain-specific color maps or maybe have something higher level that's color maps in other, to use more generally. And yeah, I think that's a good point. I think a lot about Matplotlib color maps, and I'm hoping to actually kind of tie back into Matplotlib color maps a little bit with some of this stuff that's been going on. But then, in fact, maybe the yellow, green, blue that's been repurposed here could just be the Matplotlib yellow, green, blue, and I happen to also use it for salinity. And on the other hand, while I think it's great to have good repositories of color maps for people to use, this tool like this VizCM tool is so easy to use that you can kind of whip up a good color map and be pretty confident that it's going to have certain good qualities for you. So maybe it's not bad to have a lot of color maps out there either. Kelsey.
Yeah, your modified yellow, green, blue looks a lot like the Uranus.
Yeah.
Is it? So I assume it's pretty close to it.
I think it's very close. It's not purposely the same, but yeah, it's basically similar. Yeah.
So Rich Signal just used that color map in a plot of ocean temperature in his talk a couple of talks ago, and I thought it didn't show contrast very well in his case. I don't know. I think you were there. I don't know if you noticed whether is that not useful for temperature, or was that just a scaling issue, or
Yeah. I don't, I was thinking that when I saw it too. I think, and the question was, how good are all the color maps necessarily for showing a lot of detail in the images that you're showing, and particular Viridis, the new Matplotlib default. There's a lot of different directions to go with that. I think I would need to see seeing his plot in black and white or grayscale would be helpful to see how much is just the information and how much is the color map. And there are different things to think about for that more nuanced topic of, you have certain qualities that are good in your color map. There are other qualities to consider, and you'd like to be able to see as much detail in your color map as possible. Certain things are better for that as well. Green actually is supposed to be better for being able to see detail, whereas red is supposed to be worse, for example. So I don't know the answer to that question, honestly, but it's something that I've been thinking about as well, and I think is being explored in some of these tools like the VizCM tool a little bit. Okay, thank you.
Thanks, Kristen.